Namaste everyone. Hope you are doing well. Even though we are calling it as binding energy curve, it is actually binding energy per nucleon. So we have seen that when nucleus is formed, some amount of mass, a little bit of mass is lost, and that mass is converted into energy while forming the nucleus. So energy required to form the nucleus starting from individual protons and neutrons, that is called binding energy, or energy required to break a nucleus is called binding energy into individual protons and neutrons. And energy equivalent of mass defect is also called binding energy. Remember, mass defect itself is not called binding energy because mass defect is mass. It can be expressed in either kg or atomic mass unit. Its energy equivalent is binding energy. So what is mass defect? Mass defect is the Z into mass of protons plus A minus Z into mass of neutrons. This is what is expected mass of nucleus. But what happens is mass of the nucleus is not of this much, and it will have little bit of less mass because some mass is lost in the form of energy. So this difference is called mass defect. So if you convert this difference into energy, that gives the binding energy. So delta m, if it is in kg, then delta m c squared. If this is in kg or gram or something else. Suppose if you want to try to put the mass in atomic mass unit, what you can do? So 1 U is how much? 1.67 into 10 to the power minus 27 kg. This is the mass of 1 U in kgs, and it yields to, so 1 U is equivalent to 931.5 million electron volt of energy in MeV if you want to write. So 1 atomic mass unit yields 931.5 million electron volt of energy. Suppose you lose 10 U, then it is 10 times this much. That's what you can do. So direct multiplication is possible. Okay, now if you calculate the total binding energy of any nucleus, that doesn't give you the exact idea of the stability of the nucleus or the strength of the nucleus. If the nucleus has to be tested for its stability or its strength, you will have to check binding energy per nucleon. So what is binding energy per nucleon? The total binding energy per mass number. How many people will enjoy that binding energy inside the nucleus? That counts. So binding energy per nucleon is called specific binding energy, and that has to be calculated. So a nucleus may have high binding energy. For example, uranium has more binding energy, but there are many protons and neutrons inside the nucleus. 235 protons and neutrons. Mass number is 235 or 238. Its isotopes. And so per nucleon, whatever the energy available is much less. So it is not stable. So that is what you have to calculate. So if you draw a graph of, these are all the things which you have come across in the previous class. So if you draw a graph of binding energy per nucleon, this is the area where you usually go wrong. You do everything proper in the examination, but you forget to write binding energy per nucleon here. You simply write binding energy. That is very much wrong, and you will lose all the marks. Binding energy per nucleon and mass number. Okay. Yeah, and sometimes you write it as atomic number. That is also wrong. So a graph of binding energy per nucleon versus mass number, a graph will be obtained like this. You will have a sudden hike in the binding energy per nucleon, and again another hike and another hike like this, and then a high value of binding energy per nucleon and then decrease like this. This is the binding energy per nucleon curve versus mass number. Very important curve because this gave answer to many questions in the nature which were unanswered. The highest binding energy lies for 8.75 million electron volt, and this is in million electron volt. I don't write the unit here. 8.75, and that lies for iron. Iron is the strongest element. Even calcium is strong, and that because the specific binding energy or binding energy per nucleon for iron or calcium is very high. That is the highest one. And here are some spikes which say that binding energy per nucleon is not varying smoothly with the neighbors. Suppose the binding energy of lithium is something, then beryllium will not be the same as its neighbor lithium. So there will be much difference. There is a high sudden increase and decrease. So this is lithium, nitrogen and oxygen. So like this. So it should move forward, oxygen. And what about this one? Helium, carbon, oxygen. This is oxygen 16. This is another isotope of oxygen. So this is the value which is very less value for oxygen compared to oxygen 16. And compared to nitrogen, the value for carbon is very high. Nitrogen will have this value, whereas carbon will have high value. See the sudden increase and decrease in the specific binding energy or binding energy per nucleon here in this range. But such spikes are not found anywhere else except here. So this is one range, and what about here? See uranium, say F234, then okay, uranium 235, something like this. It is not stable. Its binding energy per nucleon is less. So what are the features of the binding energy curve? Once you draw all the binding energy per nucleon for different elements versus mass number, you get a curve like this. So what is the conclusion of this curve? Very simple. The curve says that for elements which have mass number very less, for example 10, below 10, the elements lying below 10, they have very less specific binding energy, which says that they are very unstable and their nuclei is not very strong. So elements having very less mass number below 10 are unstable. Their binding energy per nucleon is very less. Elements having mass number very high, say greater than 170. So let us have a range between 30 and 170. Mass number between 30 and 170. Elements having mass number between 30 and 170 have less binding energy per nucleon. They have high binding energy per nucleon. Elements lying away from this or outside this range have less binding energy per nucleon. So elements having mass number between 30 and 170 have binding energy per nucleon a little bit very high. So greater than some 7.5 million electron volt, and the highest lies for 8.75 million electron volt. That is what you call iron. So binding energy per nucleon for elements lying between 30 and 170 is fairly high, and it is more than 7.5 million electron volt. This one. So here if it is 30 and if it is 170 somewhere here, for them it is greater than 7.5 million electron volt. And binding energy per nucleon is very high for elements, very high for iron, calcium, etc., lying approximately at 8.75 million electron volt. And binding energy for elements having high mass number is also less, low mass number is also less. So why this is so? The reason for this, the reason for the nuclear processes occurring in the nature like fission, one, nuclear fusion, and all these, why this occurs in nature, that answer for all these questions was given in this graph. How? Why does fission occur? Why heavy elements when they are bombarded with neutrons split into two? So breaking up of a heavy nuclei, thereby forming two daughter nuclei which are stable. Heavy nuclei is unstable and the daughter nuclei is very stable. Why this happens in nature? Heavy nuclei which have high mass number, they are unstable. Reason is they have many protons inside. The repulsive force between the protons will become a little bit predominant, and the nuclear, the binding energy will be binding energy per nucleon will be less. So elements having very high mass number are unstable. How do they become stable in nature? By splitting themselves into two lighter nuclei and which have lesser mass number, and they come here. For example, uranium splits into two elements like barium and krypton, for example. Need not be always barium and krypton. Suppose uranium splits into barium and krypton. Barium and krypton are stable. So fission is a process where a heavy unstable nuclei split into two lighter nuclei of comparable masses, and these lighter nuclei will be more stable. And the proper explanation for why fission occurs in nature is given here. So once they are lighter nuclei with the lesser mass number, they come under this category here, and their binding energy per nucleon will be high. One reason. Second one, Why lighter? What happens to the elements having very less mass number? What happens to them? Elements having very less mass number, they combine together to form a heavier nucleus. That is what you call fusion. Fusion is a process where lighter nuclei combine together to form a heavier nucleus. So once they become heavier, suppose for example hydrogen and hydrogen combine together form deuterium, deuterium nuclei combine together to form helium, and then they become stronger. So elements having very less mass number are unstable, their nuclei is unstable, and they have less binding energy per nucleon. In nature what happens is they combine together and they become a heavier nuclei, and that lies here again, so their binding energy per nucleon will be more. So fusion gives a stable nuclei. Fission gives a stable nuclei. Heavy elements undergo fission and become stable. Lighter nuclei combine together and become stable. And we have a liquid so we have a model called liquid drop model which explains all these things. But a liquid drop model was not successful in explaining all the nuclear phenomena. Whatever is happening in nucleus, everything is not explained in liquid drop model. So, but to somehow why fission and fission occurs is explained in liquid drops. Suppose you have small liquid drops, very small liquid drops, they are unstable. They combine together to form a bigger drop. Suppose the drop is too much bigger, it splits into smaller drops so that it becomes stable. So everything is explained in the graph itself. So graph itself is self-explanatory, and you can give all the answers to the questions of fission and fusion. So you may be asked to write the features of this binding energy curve. So what is binding energy per nucleon, or specific binding energy? Draw the specific binding energy curve and explain the features. So binding energy per nucleon is called specific binding energy, and the graph is like this, and this graph clearly indicates that the first point, elements having less mass number are unstable and their binding energy per nucleon is less, and elements having high mass number are again unstable, they have less specific binding energy here, and elements having mass number between 30 and 170 are very stable, they have binding energy per nucleon greater than 7.5 million electron volt, and element like iron will have very high specific binding energy which is very strong in nature. And the reason for fission is given in the graph, that elements having high binding energy, high specific binding energy like uranium, they split into two and become stable, and they come under this group here. And elements having very less mass number are unstable, they combine together, they undergo fusion and they become stable. So everything is explained. So very important curve. Okay, now we will see what is fission. Okay, so fission is a process that is happening in nature where heavy nucleus breaks up into two lighter nuclei, and those two lighter nuclei will be stable and their masses will be comparable mass products we will get. And best example is uranium. Suppose you take uranium 235, 92 atomic number, mass number 235. Its nucleus is not stable, it is not very strong, its binding energy per nucleon is very less, but binding energy total will be more. But binding energy per nucleon, when you divide it by 235, you will get per nucleon value very less. So it is unstable. Now we will make it more unstable by putting one more neutron into the nucleus. So take a high kinetic energy neutron and make it, we use a word called bombarding. Bombarding means a fast moving neutron is made to hit the nucleus. When it hits one nucleus of uranium, you get one more neutron inside the nucleus. So when a fast moving neutron is made to hit the uranium nucleus, it enters into the uranium nucleus. Now the new element formed is 236, right? It is balanced, correct? Now this nucleus is not stable. At any moment it can break up because its binding energy per nucleon is very unstable, very less, and there is no stability inside the nucleus. So it breaks up into two elements. One is barium, 56 barium 144 plus another one krypton. This is one example where it can happen. So the thing may not be the same in all the cases. All the uranium may not yield the same products. But one example I will take, 36 krypton 89 I will put, and neutrons, some 3 neutrons are produced. Okay, so better you remember this example because it may be asked in the exam. Give an example for fission. So take uranium-235, bombard it with the neutron. When neutron goes and gets itself into the nucleus of uranium, you will get a new element, uranium-236, and barium plus krypton plus 3 neutrons. Okay? So is it balanced now? 236 here, 92 here. What about here? 144, 153 and 233 plus 3 neutrons. So 3 neutrons, 3 into 1, 3. 236. What about this one? 56, 62, 92. Yes, 0. So 92. It is balanced. Now if you observe this, large amount of energy is also released. Say for example, almost 200 million electron volt of energy is released, say, if it is so. From where do we get that energy? This is another example for Einstein's mass energy relation, where energy is converted into mass. This is another example. How do you explain so? You calculate the mass of the reactants, get the mass of the products, then surprisingly you will find that the mass of barium, krypton and 3 neutrons is lesser than the mass of uranium and this neutron. Uranium and neutron together make more mass, and barium, krypton and 3 neutrons make less mass. So there is a mass difference, mass defect. So if you are asked to find out mass defect, what you have to do is add the masses of all the products, barium, krypton and 3 neutrons, subtract it from the total mass of the reactants. You will get the mass defect, convert it into energy, you will get this one. Of course we are going to work out problems on that base, right? Okay, so this is the energy obtained, and that yields a large amount of energy. And remember, when a nuclear fission is taking place, whether it is in a nuclear reactor or a nuclear bomb, controlled or uncontrolled, whatever it is not the single nucleus which is breaking into lighter nuclei. Because when you take the sample, you don't take the one single atom. It is very difficult to take one single atom. You take a sample of uranium. Suppose you take 1 kg of uranium. It contains so many atoms, right? It doesn't contain a single atom. So when so many atoms are taken together, when you hit one neutron to one nucleus randomly, and that neutron goes to that nucleus and it enters the nucleus and it creates instability, and that gives the products and a large amount of energy. Now along with that energy and the products, you see 3 neutrons are produced. I think you can see this, right? Yeah. 3 neutrons are also produced. What do these 3 neutrons do? They don't simply keep quiet. They are moving, fast moving neutrons. They hit 3 more uranium nuclei, because you have taken a sample of uranium where it is in grams or kgs, and it contains plenty and plenty of uranium nuclei. For example, if you take 235 gram of uranium, it contains Avogadro number of molecules, correct? So so the 3 neutrons released, they bring fission in 3 more uranium nuclei. And if those, if I can write this one, you might have seen this chain reaction process anywhere. So suppose this is uranium-235, 1 uranium-235 atom in the cluster of uranium that you have taken, 1 neutron enters and hits this. It gives 3 neutrons, right? 3 neutrons are released. What do these 3 neutrons do? Do they keep quiet? No. They will go and hit 3 more uranium atoms. Uranium, uranium, uranium. And here again 3 more neutrons are released, like this. Now it is 9 neutrons in the 3 process. If you take the highest possibilities, there will be 9 neutrons. What these 9 neutrons will do? They won't simply keep quiet. They keep on producing instability in 9 more uranium atoms, because many uranium atoms are available in the sample. There is no scarcity of uranium atoms. These 9 fissions again, they yield to 27 neutrons. I need not explain it. Now it is like, this is called chain reaction. So every time if you want to bring the chain reaction, you need not take a neutron one by one and hit the neutrons. As you take mangoes from a tree, you have to hit each mango with each stone. But here it need not be so, because each mango yields 1 more stone. So the 3 more stones, and those 3 more stones will take up 9 mangoes, so something like that. So fission process produces some fast moving neutrons, and these neutrons hit a few more uranium atoms and uranium nuclei and bring a fission in them and release 3 more in each. That produces 9 and then 27, then each 3, 27 into 3 like 81. So like this way it keeps on growing, and this is an uncontrolled process finally. Remember, each process gives this much of energy. When this happens within a fraction of a second, large amount of energy is released, and that is called uncontrolled chain reaction. So chain reaction is a process where neutrons produced in one fission reaction, and they continue the chain reaction by hitting themselves to few more neutrons and thereby producing many neutrons. So it is a self-growing chain reaction, and it is called uncontrolled chain reaction. And if you want to control the chain reaction, what you have to do is you have to control the neutrons. You should stop the neutrons which are bringing further chain reaction. That is the only way of controlling this one. So fission chain reaction is a process where fission chain reaction. Fission chain reaction is a process where neutrons produced in one fission process will bring fission in another uranium nucleus and makes the chain reaction to makes the fission reaction to grow, and thereby releasing large amount of energy in a fraction of time. This is the process involved in nuclear bomb. We use fission for constructive as well as destructive purpose also. If it is a bomb, it's uncontrolled chain reaction. What do we do in nuclear reactors, where it shouldn't explode, it shouldn't give energy all of a sudden, and that energy, same amount of energy, should be continued for a long length of time. If the energy is released like a bomb all of a sudden, how to make use of it? It creates destruction. And if you can take that energy little by little for a long length of time, it is constructive. You can use it for a long time and it will not be destructive then. So how to do that? In order to do it, you have to control the number of neutrons. And nuclear reactors employ control chain reaction. They use control chain reaction. How? By absorbing neutrons. And we have all the arrangements in the nuclear reactors, and you might have studied that diagram and all. I don't go for that nuclear reactor completely. They have control rods. What are control rods? Control rods are the rods which are introduced and taken away from the nuclear reactor core. Right? In a nuclear reactor, there is the central part of the nuclear reactor where chain reaction is taking place. And if you want me to explain it in short, there is and I will show it. This is the core, and it is made up of concrete walls. These are all concrete walls, because when a nuclear chain reaction takes place, there are so many problems. The products obtained, what I have written, for example, barium and krypton, those products are highly radioactive. What do you mean by radioactive? They emit harmful radiations like alpha, beta and gamma radiations. Gamma radiations are very hazardous, and they create so many problems, and they are also creating some genetic problems. So problems will be carried to the offsprings and the later generations, and that's why the people working in the nuclear reactor must be protected from all those things. So the whole chain reaction, control chain reaction, is occurring within a concrete wall, and there are some control rods here. And of course, all these are controlled and introduced inside and taken outside using all mechanical and computer processes, and no people will be involved in this. What are control rods? Control rods are one which can absorb neutrons. And if the chain reaction is going out of control, that means beyond the process, these control rods are put in. Neutrons are absorbed, so that chain reaction is controlled. Because if you go, for example, in each chain reaction, for example, one neutron hits one nucleus, say, it brings 3 more chain reactions, fission process. And those 3 more fission processes produce 3 neutrons each, so you will have 9 neutrons coming out. And if that 9 neutrons, again they bring fission in 9 more nuclei, 27 neutrons are produced. Out of 27, absorb 18 neutrons, you will have 9 only now, active. Again, those 9 neutrons go and hit to 9 more uranium nuclei, 27 neutrons are produced. Again, absorb 18 neutrons. So you can control the chain reaction, and sustained chain reaction can take place. What do you mean by sustained? Energy is distributed in a uniform way, and that is not exploded. And the chain reaction will not explode, or it will not grow like multiples of 3 or multiples of 2. So it will be controlled, and that is what is done in control rods. And that control chain reaction yields a lot amount of energy, and there will be energy in the form of heat also, and there will be some coolants, right? What are coolants? Heavy water or some liquid will be circulated inside, and when it passes through the core and comes out, it gets heated and it gets converted into steam, and the pressure created by the steam is used to run the turbine, and we use it for electricity and any other constructive purpose. Of course, you should have a coolant, and there are some materials used inside called moderators. What are moderators? Moderators are the elements or the parts we used in the nuclear reactor to slow down the fast neutrons. Because for most of the nuclear reactors, we depend on uranium. Uranium is the easily available raw material for fission, but not uranium-235. Uranium-235 is not available in abundance. But uranium-238, it is an isotope of uranium. It is abundantly available. But unfortunately, this doesn't undergo fission for fast neutrons. What do you mean by fast neutrons and slow neutrons? Neutrons having some energy, certain amount of energy are called slow neutrons, and beyond that beyond certain amount of energy we call it as fast neutrons. Now, neutrons released during one fission of uranium, they are very fast neutrons. But uranium-238, if this is the raw material used here, what happens is, if fast neutrons go and hit the uranium-238 nucleus, they come out of it and they don't produce any fission. Suppose, for example, if you want to hit a bullet inside a ball, cricket ball or a tennis ball, say, you have to hit the bullet into the tennis ball with a proper speed. If the speed is more than the required one, the bullet will come out of the other side, right? I think it is a very easy example, you can understand. So if the speed is more than a certain critical value, the bullet will come from the other side. If you want the bullet to be hidden inside the tennis ball, you have to hit it with a certain range of velocities. Similarly, if fission has to occur in uranium-238 nuclei in the other atoms, the speed of the neutron which is hitting it should be of proper value, and it should have certain kinetic energy. If the energy is too high, if the speed is too high, if they are fast neutrons, they don't bring about any fission in the other uranium nuclei. They simply escape away. They don't keep themselves inside the nucleus. Instability is not continued. So, in order to make them to produce fission in few more uranium atoms, they must be slowed down. If they are allowed as it is, if they are very fast neutrons, they don't bring about fission in the other uranium atoms. They must be slowed down. How to slow down them? Moderators. Moderators slow down the fast neutrons. So, a nuclear reactor, if it is using uranium, it must have a moderator. Moderators slow down the fast neutrons. Control rods absorb the neutrons, thereby control the number of neutrons. They are not controlling the speed of the neutrons. They control the number of neutrons released, and they will control the chain reaction. They won't allow the chain reaction to grow beyond a certain limit. These absorbing control rods, whereas moderators slow down the fast neutrons, and thereby they facilitate the further chain reaction. So, a chain reaction can grow up and end up with the explosion, releasing energy in a large amount in a short time, like nuclear bomb. A nuclear fission chain reaction can be controlled by controlling the number of neutrons. Sometimes the nuclear chain reaction may not occur, and because the neutrons released in the sample may escape away. More number of neutrons will be escaping, less number of neutrons will be remaining in the sample. That doesn't bring a further chain reaction, and the chain reaction may stop. That is also possible. If the number of neutrons produced are less and the number of neutrons escaping are more, then the chain reaction will be stopping in the further process. So, in order to define it, whether the chain reaction is growing or whether it is sustained, whether it is decreasing, we have a factor called multiplication factor. What do you mean by multiplication factor? K. It is a ratio. Multiplication factor K is defined as the ratio of number of neutrons produced in present generation. I will number of neutrons produced in present generation. Present generation means when you look into the fission process, at this moment how many neutrons are produced? If it is more than the preceding generation, that means previous generation, then it is growing, right? If you have scored more marks than the previous one, you are improving. That's what we say. So if the number of neutrons produced in present generation is, it is the ratio of number of neutrons produced in the present generation to the number of neutrons produced in preceding generation. This is the definition for multiplication factor. So multiplication factor in a chain reaction is defined as the ratio of number of neutrons produced in the present generation, whatever you are observing now, to the number of neutrons produced in the preceding generation. That ratio is called multiplication factor. And if multiplication factor is equal to 1, what do you mean by that? Then the number of neutrons produced in the present generation and preceding generation are same. That means you are controlling the extra neutrons which are produced. In every chain reaction, you are controlling the extra neutrons and thereby maintaining the number of neutrons same. That is a control chain reaction. For control chain reaction, K is 1. And if K is greater than 1, what do you mean by that? The chain reaction is uncontrolled because the number of numerator should be greater, denominator should be lesser. Number of neutrons produced in the preceding generation is less, present generation is more. That means it is growing chain reaction and it is uncontrolled. So if K is less than 1, what do you mean by K is less than 1? If the multiplication factor is less than 1, then the number of neutrons produced in the present generation will be less and you are scoring less mark in the final exam and more marks in the previous exams. Your performance is getting poorer and poorer. So that is a chain reaction which is going to be stopped. A chain reaction which will end up finally end up not in explosion with no energy released. So finally it will stop. So it is a chain reaction will stop. So this is the next process. Okay. So in nuclear reactors, what the people will do, the engineers and the scientists, the core, what I have drawn, that concrete place and where the chain reaction is taking place, where we take the raw material like uranium and thorium and those things. When that material is taken, the size of the core where we put the raw material, size of the core should be of a certain value called critical size. Of course, this is not in the syllabus. What do you mean by critical size? The size of the core of the nuclear reactor. If the size of the material taken is too small, what happens is neutrons will be produced, but they will escape from the material. More number of neutrons will escape and less number of neutrons will remain inside the material, and the chain reaction will not grow. Instead it will stop. If the size of the material will be, if it is taken is material in the sense raw material like uranium, if it is taken in a large amount, more than the critical size, then what happens is all the neutrons will remain inside and that will create more number of fission reactions and it will become uncontrolled. And if the amount of material taken is of critical size only, if you take what is required for a controlled chain reaction, what you call critical size. Critical size is the minimum size, or it is the exact size for which controlled chain reaction to take place. That means in a critical, if you take the sample in a critical size, what happens is number of neutrons produced in the present generation and number of neutrons lost will be balanced and the chain reaction will be continued. As I have given in an example, when 27 neutrons are produced, suppose 18 escape from the material, then 9 will remain. Those 9 will again produce 27 neutrons, 18 will escape. So critical size is the minimum size required for controlled chain reaction. Okay, so the core of the nuclear reactor is always of critical size. So that is multiplication factor K. This is always taken into account in a chain reaction. So in control chain reaction, we use control chain reaction is used in nuclear reactors, and in nuclear bomb, uncontrolled chain reaction is taking place. Okay, so that is one. Right. I will give you a little bit of introduction to fusion, and then I will stop. Okay? Yes. Little bit theoretical. Not much. And also you have come to know about all these things in the rover classes. And even if you can understand it if you read it yourself. There is no much some techniques involved in this, just like a story. Okay. What is fusion? Fusion is a process where two lighter nuclei combine together to form a heavier nucleus. Best example is 1H1, two hydrogen nuclei. This is what is happening in stars. The sun is giving so much of energy from billions of years and still giving energy, and it will continue for so many billions of years. From where that raw material and what is burning there, how do we get so much of energy from the sun? It is the fusion process occurring in the stars and sun, even including sun. What type of fusion? Raw material. Sir, do we have so much of raw material in the sun? Yes, hydrogen is available in plenty in stars. Because stars themselves are formed, the new star will be born only when the hydrogen cloud come together, right? And from there it starts, the birth of a star. When hydrogen gas or clouds come together, the birth of a star takes place. So hydrogen is available in stars in plenty. So what is there to think about the raw material? Plenty of hydrogen is available, and these hydrogen and hydrogen, because of gravitational force, and they come closer, they collapse, and temperature increases, they fuse together. And remember, if two hydrogen nuclei have to come together, they are positively charged. It is not so easy to fuse two nuclei together. And if two hydrogen nuclei have to be accelerated to a very high kinetic energy, and if they have to fuse together to form a deuterium nucleus, say 1H2, again another isotope of hydrogen, high kinetic energy must be given for them, and that is possible only when the temperature is very high. And such a high kinetic energy is possessed by two nuclei only at high temperature. So for fusion to occur, you need high temperature. Sir, whether that high temperature is available in stars? Definitely, because when the hydrogen clouds come together, close together, temperature increases, and that temperature is suitable for this fusion reaction to take place. But from where do we get energy? Okay, fusion reaction is occurring. Some amount of mass again is converted into energy. So this yields to hydrogen gives rise to deuterium plus some amount of energy. In between, you will find that there are some more particles emitted. One is positron. What is positron? It is the antiparticle of electron. What do you mean by antiparticle? The particle which has got the same mass but opposite charge. And there are some more conditions for antiparticles. If a particle has to be an antiparticle of another, there are so many conditions. But for the time being, see, proton is not the antiparticle of electron. Positron is the antiparticle of electron. It has the same mass and opposite charge. For the time being, it is enough. Since a positron has same charge but opposite in nature and same mass, now we can call it as an antiparticle. Such a positron is emitted, very similar to electron but positive charge. So deuterium plus positron plus another particle called neutrino. So nu. Okay, this is neutrino and this is positron, and this is some about 0.42 million electron volt of energy. As I remember, 0.4 something, 0.4 million electron volt, and I will check it later. So this is positron and this is neutrino. So these particles are also emitted. We will come to these particles. Sir, from where do we get all these particles? And how do the scientists came to know that these particles are emitted? Because they balance the equation. And if hydrogen has got some energy, this hydrogen has got some energy. When they join, whether the energy of this deuterium and the positron is same as this energy, and if you add all these three energy, some energy is missing and some particles should be coming out. That's how this neutrino was detected. So there are some conditions for the equations to be satisfied. When it is not satisfied, they search for some other thing. So they come to know that one more particle is emitted, one more balancing, suppose you balance the charge, one more particle has to be emitted, something like that. Okay, for the time being, you take this as a nuclear reaction, that is fusion reaction. So fusion is a process where two lighter nuclei combine together to form a heavier nucleus. When they form the heavier nucleus, certain amount of energy is released. Okay. now they become stable. Of course, deuterium is also not completely stable. In stars, what happens is once hydrogen and hydrogen combine together to form deuterium, then deuterium and deuterium will combine together to form helium. 1H2 plus 1H2 will give you 2He4. Balanced again. So they will give helium, and helium will combine together to form carbon, oxygen, and finally it will end up with iron. So this is happening in stars, but stars will give continuous amount of energy. And if you read the birth of a star and the death of a star, death will occur for a star in different ways. Maybe in the form of a black hole, or maybe in the form of a supernova explosion, and you can study it later. But the main thing here you have to remember is, it is the fusion reaction which is taking place in the stars for the production of so much amount of energy, and raw material available for the fusion reaction is abundantly available in stars. And another thing is high temperature available for the fusion reaction, and that condition is not required for fission. In fission can occur even it doesn't require any high temperature, but fusion requires high temperature. Fission doesn't require high temperature. That's why fusion is also called thermonuclear reaction. Maybe a question also. Why fusion is called thermonuclear reaction? If two nuclei have to come closer with high kinetic energy and join together, fuse together, high temperature is required in the surroundings, and that's why fusion reaction is called thermonuclear reaction, because high temperature is required. So if you have fusion bomb, there are two types of bomb: fission bomb and fusion bomb. If you want to have fusion bomb, you must go for fission also. First you have to create fission and develop a high temperature, then you have to go for fusion. But one advantage with the only fusion is the products obtained, like deuterium, helium, carbon, they are all not radioactive. Whereas the products obtained in fission reaction, they are highly radioactive. That's why people oppose nuclear bombs, fission bombs, because once the bomb is exploded, large amount of light, heat, sound energy is released, people will die. That's gone. Okay. What about the second part? The remaining people can't go there because it is full of harmful radiations. And those who get affected with harmful radiations, they are also affected, and people who live there will be affected, and their next generation will also be affected, because those radiations they cause genetic mutation, and they will cause problem in the cells, and which will be carried to the offspring's next generation. So that is harmful not only to the people who are now living, and also to the people who are going to give birth or who are going to be born in the later stages also. They will also be affected. So that is why it is a most dangerous one. But that is nuclear fission bomb. Whereas in fusion process, the raw materials, the products obtained are not radioactive. Even in nuclear reactors, when a nuclear reactor unit is opened in a certain place, people they oppose it. They protest it, because the byproducts obtained after carrying all the process there shouldn't be thrown away outside. It is most dangerous. If it is put in a river, if it is put into the sea, then all the living beings in the sea, like fish or anything, they get affected, and if we eat it, we also get affected. So there are some particular international rules, the way in which these byproducts, not in these byproducts, the products obtained in the nuclear fission in a nuclear reactor obtained, they must be put in a deep ground, buried in concrete tanks, right? Concrete tanks must be built up, they must be put in the deep ground, and even in the place where there are no habitants and no people are living. So in such there are some conditions, and in some places but don't know whether the people are following it or not. So that's why people protest it to have nuclear reactors in their place. Okay, but we need energy, we need electrical energy everywhere, but we don't want nuclear reactors. Okay, that is a problem now. Okay, so I will carry on with this one in the next class. Thanks for watching my class, because already it is time, and hope you are using these classes very well. And even though it is, and one more thing, you will have a few other classes, physics, other than physics, chemistry, maths will run within 4 days. Within 4 days you will have regular classes. Right, in other subjects also. So we are making all the arrangements for it. With so many difficulties we are doing it, but still we are with you. So don't waste these classes, use it as much as possible. Thanks for watching my class. Take care of your health, that is more important. So we will meet in the next class. Thank you.